Welcome to the first ITC Pizza Lunch of 2018. The theme for this year's talk series is winds and outflows. So winds and outflows are a common phenomena in the universe, and they're relevant for astrophysical objects across a broad range of scales, so from stars and planets to galaxies and AGN. And as you can see from the schedule, throughout the semester, we will cover many different aspects of this broad topic. And the topic for today is stellar winds and how they affect stars themselves and their surroundings. So our two speakers today are Aaron Dotter and Cecilia Garraffo. They're both postdoctoral researchers here at the CFA. Aaron, who will speak first, is an expert on stellar evolution, and today he will tell us how stellar winds and the mass loss associated with them affect the evolution of stars and their environments. Cecilia, who will speak second, is an expert on stellar activity and rotation, as well as star-planet interactions. And she will tell us today about stellar spin-down models and how stellar winds affect the slowdown of the rotation period of stars. Each talk will be 20 minutes, and then we will have some time for a few quick questions after each talk. And then we'll have a longer discussion with both our speakers today after the pizza arrives. So pizza should arrive around 11:45. And then we'll take a short break, maybe 5 minutes, so that everybody can grab pizza. And then we would like to invite you to come back to your seats and participate in the discussion with our speakers, which will be moderated by Morgan McLeod here. You're very welcome to ask questions during the talks or right after the talks. But in case you have more general comments or questions that require longer answers or more open-ended, we would like to ask you to save those for the discussion. Okay, so let's get started.
All right. Thanks, Antonio. Okay, let me get rid of this. And let me get back to...
Nice beach.
That's near Bateman's Bay, which is south of Sydney. Okay. On the beach? Yeah, I think they're probably... All right, now I've lost it somehow. All right, bear with me for just a moment here. There we go. Okay. I wanted to start off... Thanks for the opportunity to speak here today. I wanted to start off with some pretty pictures because you know that planetary nebula are some of the most visually stunning images that we get in astronomy, and they're also highly relevant to stellar winds and stellar evolution, as they represent a fairly brief phase prior to the endpoint of low to intermediate mass stars, when all this material that the star has thrown off is illuminated by itself, leading to these crazy images. So, I thought that what I would like to do is just begin. Now, I should preface all of what I'm going to say by pointing out that I'm not an expert in stellar winds or mass loss. It's an area that I appreciate very much, but I don't consider myself to be expert in it. So I'm just going to give you a sort of a general overview of the different types of winds that we know about and which are more important for different types of stars. And then we'll go into looking at how those winds influence stellar evolution, which is something that I can speak on more comfortably. Okay, so I'm going to first of all break things down between hot stars and cool stars, and if you like to draw a line somewhere, let's say 10,000 Kelvin is your hot to cool transition. Hot stars tend to be also quite luminous, and because they're hot, they have a hard radiation field, meaning that they are bright in the ultraviolet, maybe even into the X-ray. And so one of the important consequences of that in terms of the stellar spectrum, the emergent spectrum, there is, in the ultraviolet, there's a lot of line opacity in metals, particularly. There's not a lot of continuum opacity relative to the amount that's in the lines. And so the winds that occur in hot stars, particularly, are what we call line-driven winds. So the atoms are actually being pushed away by radiation pressure. And so mass loss in hot stars tend to be massive stars, and they tend to also be rotating rapidly, and rotation modulates that mass loss. There's even a sort of category of stellar winds or stellar mass loss that is mechanically driven. That is, the star is rotating near the Keplerian breakup limit. It can actually push material off in order to sort of keep it from going over that limit so that it doesn't break up. A typical example of a hot star that's losing tremendous amounts of mass are the Wolf-Rayet stars, which are post-main sequence massive stars. They are starting to show the products of hydrogen burning in the envelope of material that's being thrown off by the star at a tremendous rate. Okay, so now let's switch over to cool stars. And when we're talking about cool stars, we're really mostly talking about, in this case, the giants, because the cool dwarfs, relatively speaking, aren't losing much mass. Their winds, it's not to say that they don't have winds, but their winds are not strong, and they're not really driving the evolution of the star in any measurable way. So these objects have, because we're talking about cool giants, they have low surface gravity, and many of them happen to be pulsating. And because they're cool, it's also possible for dust grains to form, and we at least think that the dust grains are what are carrying the material away from the star in some fashion, driven most likely by these pulsations. So the types of stars that we're talking about here are usually called long period variables, which is the LPV acronym. The MIRAs are a category, a commonly named category of those. So most of what we deal with in terms of stellar evolution models are simple prescriptions because first of all, in terms of theory, we don't have much in the way of real actual theory that describes particularly how cool stars lose mass. Hot stars, you can do first principles, physical calculations that describe the line-driven winds, and many people do that. There's a whole field of a whole body of work in the literature about line-driven winds and the calculations of those. But on the cool star side, we don't have that advantage, and so we are looking at some kind of description based sometimes on observations, mainly driven by observations. And I'll come back to that point in a moment. But a lot of what we're doing is really based on this formula that was derived by Reimers in the 1970s. And the key feature is that, is that the mass loss rate is proportional to the luminosity of the star. And in the case of the Reimers formula, it's a linear relationship. The radius and the mass also come into it in this particular case. And Reimers is what people who do stellar evolution calculations tend to use for the first ascent red giants. So these are the stars that are post-core hydrogen burning, but pre-core helium burning. When we move on to a later phase of evolution, the AGB, which is post-core helium burning, then the stars tend to be larger than they were during the first ascent red giant, and the pulsation periods are longer, And that's where the pulsation-driven winds can come in. And so important work in this area was particularly done by Peter Wood and his collaborators over the last many years. And typically what we find here is that the mass loss rate is proportional to the period, so longer period stars have stronger mass loss. In terms of the work by Vasiliadis and Wood, their relationship between the mass loss rate or the wind saturates for stars that are about 800 days with pulsation periods of 800 days and longer. So it rises fairly steeply until it reaches that limit, and then it sort of flattens out. Another work in this area was done by Blocker back in the mid-90s, same as Vasiliadis and Wood. And they basically, their mass loss is multiplied by the Reimers formula. So what it does is it adds a stronger dependence on the luminosity. For the hot and massive stars, it gets really complicated. There are lots of different temperature dependencies, and if the star is a Wolf-Rayet star or not, so if it has hydrogen-burning products at its surface or not, the mass loss rate will vary. There's a great review article from Nathan Smith from fairly recently that will tell you more about that if you'd like to learn more. And this is all complicated by the fact that although there are observers in the audience, and I'm thinking particularly of Andrea here, who have worked on mass loss in the past, it's not possible to go out and actually measure a mass loss rate, right? You got to you're measuring something, and then you're tying that to a wind, for example, by hoping that Andrea will talk about this more later in this series. So let's move on to more comfortable territory for me. Talk about how stellar evolution models vary as we include mass loss, and if we change the mass loss rates, what happens. So to begin with, no mass loss yet, it's here, but we're not showing it explicitly. I have a series of isochrones from the MIST project, which is something that's worked on by myself, Jian Choi, Charlie Conroy, and various other people here at the CFA. HR diagram here, this is for solar metallicity initially stars, and over a very wide range of ages from 100,000 years to 10 billion years, or maybe slightly more than that. So here's a very old isochrone. There's the main sequence turnoff, the red giant branch. And what I've done here for this plot is I've cut out the post-AGB phase for the low mass, for the older stars, because that sort of lives in this area, and it gets in the way of the main sequence in the younger stars. So the color coding here, yellow is very young, and all the way down to the black ones here, which are very old. So identifiable features, there's the main sequence sort of setting the blue or the hot edge of things here, and then the post-main sequence evolution fills in this area here. In the older populations, you have the red giant branch, which is easily identifiable. Okay, and so we're going to, for the next few slides, I'm going to focus on these types of things, or these types of diagrams. So here's a plot where now I'm showing the same isochrones again. Main sequence here, the red giants are over here. And now the color scale is the mass loss rate in terms of logarithmic, and it's the absolute value because we're really talking about a negative value. dm over dt is less than 0. And it's reported in solar masses per year, which is the typical scale for mass loss rates. And what you can see is that really there is a very strong dependence here on luminosity. That's the main thing that's driving the stellar winds in all of these different relations that we use to calculate what the mass loss rate should be. And regardless of the temperature, when you get up into the most luminous stars, it's very strong. It's up around 10 to the minus 5 or 10 to the minus 4 solar masses per year. Here's what we get if we take, instead of the solar metallicity models that we've been looking at previously, if we go down to a lower metallicity, Fe over H of minus 2, same range of ages. Qualitatively the same, but if you kind of flick back and forth, you can see that perhaps these objects, at least at the young ages, get brighter, and the mass loss is slightly stronger. So most important conclusion to take away so far, mass loss is proportional to the luminosity of the star.
So what you just showed us, is that from those models that you quoted before?
Yes. Right. Okay. So I'd never done this before, but after I made these... Yeah, sure.
So you said that this sentence is just not the same as what you said before about this first paper initially. I mean, is it not this included already in your calculations? That mass loss is proportional to luminosity.
Yes.
So how is this already? How is this again a conclusion of the work if it's already included?
This is a takeaway message.
Okay.
Not a... I'm not concluding based on these diagrams. I'm showing the outcome of putting in mass loss rates like the one that I talked about initially.
So it's Reimers. You use a Reimers with the.
Well, Reimers is over here. And then there's other stuff going on for the AGB stars. We use the blocker. And then for the...
So you use different laws in different.
Yes.
Okay.
It's not just Reimers, but Reimers shows the luminosity dependence, and sometimes it's even stronger than in the Reimers case, which is a linear. Okay, so if you just want to take one thing away from this talk, it's that. And so I thought what I would do, this is just kind of a curiosity, right? This is not the HR diagram, but it looks an awful lot like it. Instead, I plotted the mass loss rate. And now the color scale is back to age again. So the yellow lines are the young ones, and the black lines are the old ones. And, yeah, it's just kind of in these models, we provide lots and lots of information. And a lot of times no one's ever plotted X versus Y before. And this is just another way of demonstrating that the mass loss rate is primarily proportional to the luminosity. You can see some detail here that something's happening around 10,000 Kelvin, and that is that we're switching from one rate to another.
What is black? Black, I thought was the
Black-
highest rate.
Sorry, we're switched back to age now for the color scale here. So the black ones are the old ones, and the yellow ones.
Age, okay.
Yeah, I'm jumping around in color space. Okay, so let's take a look at individual stars now. Here's a one solar mass, solar metallicity evolutionary track, starting from the pre-main sequence contraction over here to the main sequence over here, the red giant branch, the core helium burning phase, asymptotic giant branch, and the white post-AGB and white dwarf cooling tracks. And what we have here is our preferred mass loss prescription, which is Reimers for the red giants, the first ascent red giants. It's blocker for the AGB stars. And so that's the blue line, which is more or less covered up by the other two. That's your preferred scale. And then the cyan track here is half of so everything, all the mass loss rates have just been halved. And the sort of medium blue color, all the mass loss rates have been doubled. And really, for this star, it doesn't make much difference. And we'll come back to that in a moment. Here's a 10 solar mass model now. Same colors shown, and for the most part, it looks basically the same. You're starting to see a little more activity even here, a little more differentiation in the HR diagram. But now let's focus in on the helium burning phase, which is these loops here. Twice the normal rate is right here. and the normal rate and the half the normal rate are over there. So that's a huge difference, right? That's very significant. And that, if we look at young populations that might have, such as, nearby galaxies that have recent star formation that could have 10, 15 solar mass stars in them, and we see them extending over here, that gives us a constraint that our mass loss rate is not off by a factor of 2, at least in one direction. And now we get to, I'm going to go up a factor of 10 again to 100 solar mass. Part of what we're saying here is that we really don't know, we don't really have very much constraint on how 100 solar mass stars evolve. But, so this is the beginning of core hydrogen burning right here. And everything that happens after that, there's a variation for a factor of 4 in mass loss rate. There's a factor of 10 in the final luminosity of the star. So that's tremendous, right? That's a big, big difference. And then here I've put them all together. And now we're talking about the stellar lifetime. There's a difference at the 100 solar mass track. The difference in the stellar lifetime is about 10% from the half to the default value to the twice the default value in terms of mass loss. So not only does it affect where the star is going in the HR diagram, but it also has a not inconsiderable effect on the lifetime of the star. If we go down to the 10 solar mass star, it's only 1%, and for the 1 solar mass star, it's only 0.1%. Okay, and that's mainly because the 100 solar mass star is very bright, and so it's much more sensitive to the mass loss. All right, same diagram again, but now I'm just listing the result in terms of the final mass of the star. So when the evolution stops, at the endpoint that we've chosen for it to stop at, the final mass in the 100 solar mass case differs by 100%. That's a big difference, right? So, and it's 10% at 10 solar masses, and it's about 3% at 1 solar mass. And, okay, so now I'm going to drop the 100 solar mass for a moment and just talk about, my final slide will be discussing the initial final mass relation, which is one of the more significant predictions that can come out of stellar evolution theory. And this is, you can compare this to masses of white dwarfs that may be measured in star clusters or in the field, but this is an important prediction of stellar evolution theory. And the different blue points here are all the same that I was using in the past too. So the sort of cyan point is half the normal rate, the blue is the normal rate, and the medium blue is twice the normal rate. So solar metallicity initial final mass relation is here, and that's the, so we're talking about stars that don't go supernova or form a black hole or something. So these are basically the white dwarf masses that you get at the end of the evolution for an initial mass between about 1 and 8 solar masses, or 7, I guess. In that case, there's a few percent variation, but I guess the second takeaway message, one, luminosity is important, and the second one is that it's really stellar evolution, the sort of laws or equations of stellar structure and evolution are what, as well as the metallicity, so the composition of the star, is really what sets the final mass. Mass loss doesn't change that very much, a few percent, but that's not a huge change compared to the difference between the solar metallicity and the -2 case. But when that material comes out, it does change, and it can change a lot. And that has important implications for things like chemical evolution, which, in the interest of time, I won't go into that. But that's all. Thank you.
Any questions for clarification, for questions now?
So I noticed on the pre-main sequence, you didn't have any mass loss. Do we expect similar, like, RGB first descent type mass losses where the pre-main sequence and the RGB tracks overlap?
Just in terms of the formula, the Reimer's formula would give you a mass loss rate there. Sure.
But do you expect that in the stars?
No. I think that's really more, I mean, yeah, maybe. The accretion is still going on to some extent in that phase, and so I think the what's going on is very different, even though the stars are sort of inhabiting a similar part of the HR diagram.
Time for one more question? Yeah.
Yeah, you mentioned that there was no sort of ab initio model for the cool giant mass loss. Does that make a difference or factor in things like dust formation in the atmosphere?
Yeah, there's been more work, and I'd say it's better constrained in terms of the AGB stars that have the long pulsation periods. In terms of the first ascent red giants, there really isn't any good theory that describes it. It's believed to have something to do with dust grains, but beyond that, there's a lot of different empirical avenues of estimating what the mass loss rate is, but there's no good theory that I'm aware of. I know. I'm gonna. Yeah.
One question before you, I'm sorry, you unplug. But on your 10 solar mass star, when you showed the difference in the mass loss rate that you assumed,
Yeah.
it looked as though it changes the luminosity substantially. And I was wondering, how does that affect the isochrone? Because that's the position, if I have the coordinates right. So in other
Yep.
words, if you use the wrong mass loss rate, you'll get a different age for the star. In other words,
Yes,
it looks
if you're
like
talking
it's
about
moving it in the-
10
in
solar
the
mass.
CMD, yeah,
Yep.
in the 10 solar mass star.
Yep, that's right.
So it's going to affect the inferred ages.
Yep.
Yeah, okay.
It
And by
is.
the way, dust doesn't really happen in the first descent giants because we see chromospheric acceleration. Stuff is going out when there's no dust. So there's something else driving it, whether it's alphane waves or some MHD phenomenon. Yeah.
I needed
Thanks so much.
connector thing.
What's that?
Do you have, what is this
What
one?
about this one?
Oh, yeah.
It's a tiny little chip.
Yeah.
Okay.
Beaches everywhere.
Yeah.
Well, it's the middle of winter. You
Right?
can
That's what keeps
take
you
what you
going.
can get.
Somebody asked me actually if my husband is buried there in the sand, but he's not. I never noticed it could look like it. All right, let me see. Does this work? Okay. Okay. Thank you for the invitation. And I'm going to talk about a very similar topic. So it's cool because it's complementary, actually. I'm going to talk about the other stellar winds, the stellar winds of cool stars that are younger, so before and at main sequence. And I'm going to talk about how understanding these winds well can we think can hold the key to understand stellar rotation of young stars that is still far from understood. And I'm going to talk in particular about a spin-down model that we've been working on. So let's start by how these kind of stars, cool stars that are younger, spin down. Okay, so these stars have a convective envelope, and they have magnetic fields on their surfaces, and these fields impulse magnetized winds through which they lose angular momentum. And that's called magnetic braking, and is a very efficient mechanism to lose angular momentum. And it's controlled, it's determined by the magnetic fields on the surface. So it's determined by magnetic activity, and it controls rotation, therefore. But in turn, rotation fuels this magnetic activity through the dynamo action. And therefore, there's a self-regulating mechanism by which stars that are spinning faster also spin down faster. And that results in a unique relationship between rotation period, age, and stellar mass. I'm showing here rotation periods with slower rotators at the top, ages in billion years, and color with low mass stars towards the right, or towards the back, whatever. And this surface, is that unique relationship, and is the basis for gyrochronology, that is this very powerful tool that allows us to translate rotation periods that we can measure to great precision more and more these days into stellar ages that are hard to determine. So this is a very powerful thing to have. Stellar clusters are coeval groups of stars, and so they lie here at constant age. These lines here are clusters. So if you look at rotation periods in stellar clusters, from gyrochronology, you would expect to see sections of this plot, sections of this surface. You would expect to see that rotation periods are a function of color, a unique function of color, and again here, slow rotators at the top, low mass at the right, and that this relationship, this is for each age, for a certain time, and that this relationship evolves with time according to Skumenich spin-down law, which is this empirical law that states that rotation periods scale with time to the 1/2. But when we do go and look at rotation periods in open clusters, we see the following. That does not describe the whole picture, obviously. So I am showing here 6 clusters, the rotation periods of 6 open clusters, from the youngest here, this way, to the oldest of 1 billion years. Again, the same axis, rotation periods with slow rotators at the top, color with lower mass at the right. The observations are in blue, and the red line is this Skumenich branch that I just described, that is what you should expect from gyrochronology. And we see that while the Skumenich branch is there, approximately, there's also a mysterious branch of persistent fast rotators that gets less and less populated with age. And there's also a gap in between the two branches that also gets less and less populated with age. And so until at the end, well, not the end, the end of this, until at 1 billion years or so, all these stars, at least in this mass range, end up already in the Skumenich branch, and that's when we think we can start to trust gyrochronology. So these pictures suggest that stars, or at least most of them, are born in this regime of the fast rotators branch and stay there for a while, and then they transition with what is a fast transition, because this gap is always pretty empty, to the Skumenich branch. And many models have tried to explain this. I'm showing here again, the top is again 3 open cluster observations, same as before, but just the 3 youngest, because you can see better the 2 branches there. And the rest are models, and the same axis than before. So many models have tried to explain this, and most of them are empirical or semi-empirical over here, and they're based on a bifurcated prescription for the torque. So they use a torque that is bifurcated, 2 different functions. And some are more physical and are based on scaling laws that date back to Cowler in the 80s, but have been improved over time. And right now, the most accepted explanation for this bimodal distribution of rotation periods is that for fast rotators, really what we're seeing that is rotating is just the convective envelope. And it's decoupled from the core. And then eventually it couples to the core, and therefore it spins down very quickly, transitioning to the top branch because of the drastic change in moment of inertia. However, recent observations have shown that this behavior, this bimodal behavior, is observed also in fully convective stars. So this argument is challenged by that. There's no core there to couple to. And more importantly, none of these models really is able to reproduce or capture the morphology of the observations. They might be able to reproduce the top branch or some particular quantities, but not the bimodal distribution, really. The first one, and only one, as far as I know, that was able to reproduce this bimodal morphology was Tim Brown in 2014 with the metastable dynamo model. Here I'm showing again all the open clusters, more of the ones I showed before, but it's the same story, going in age like this, from top to bottom and then again. No. Wait. Well, no. Yeah, like, well, it's a little bit weird. It starts here, goes up, and then. And I'm showing, so the observations are in black, in the metastable dynamo model population syntheses are in red. And you can see that he can reproduce both branches in the gap. More than the details of where the branches are, but at least the morphology, he gets it. And this model does that with a unified prescription for the torque, which is nice. And is this one. So here I'm showing angular momentum loss is a function of, well, this is a constant, this is angular velocity, and angular velocity to the cube is just what you get if you assume Skumanich, spin down. And then this is just a fitted function for color that gives you the shape of the top branch that was used by the previous model. So it's just empirical. What he needs here is that this constant takes two different values. So it's unified, it's still kind of bifurcated, but at least the functional dependence is only one. But this constant will take two different values that correspond to the two different modes that give the name to this model. And so in this picture, stars are born with their dynamos operating in a mode that is weakly coupled to the winds, whatever that means, because he admits that is not an explanation, it's just a name for it. And so that constant takes the value, whatever value here, called Km0, and then eventually, randomly and permanently and spontaneously, they transition to the other mode, which is the more stable mode, where the dynamo is operating strongly coupled to the winds. And then at that point, the stars transition to the top branch. And that transition depends on mass, the probability of that transition. So what this model, and what's important for later is that the difference between these two constants has to be 2 orders of 100 or more, so more than 2 orders of magnitude, to be able to get these two branches morphology. So what this is lacking is a physical mechanism to explain why this happens. What is that transition probability? And so, okay, so these are the models available, a summary of the models available out there. But since then, since 2014, there has been a lot of discussion about how the configuration of the magnetic fields on the stellar surface play a very important role when thinking about the stellar winds. And so as a consequence, the stellar configuration, the magnetic fields configuration has a big impact on mass loss and angular momentum loss rates. And there's been a lot of work about this lately. But all these models ignore that and assume all stars are dipolar, or at least some don't explicitly assume that, but neglect the differences. So they assume they're all the same, basically. But when we look at the data, they do not look dipolar or all the same at all. I'm showing here CDI observations. So Zeeman Doppler imaging technique is what you use to observe magnetic field maps on the stellar surfaces. These are projections in latitude and longitude of observation of stellar maps, magnetic maps on sun-like fast rotating stars. And you see that they don't look dipolar. And an increasing number of these observations show that the faster they rotate, the less dipolar they are. So fast rotating stars store a larger fraction of their magnetic flux in higher order components of the magnetic field. And so the natural question now is, what does this do to the winds? We want to know what it does to spin down rates, but they spin down because of their winds. So if you model the winds, we model the winds for stars with the same magnetic flux and different configuration, magnetic configurations. So this is a dipole, this is a quadrupole, and complexity increases this way. So this is very complex, this is a dipole, and they have the same magnetic flux. And I'm showing here only the closed field lines, just because open field lines make it very confusing. But they arise from the areas where nothing comes out, right? And so what we see is that what complexity does is close otherwise open field lines. And that prevents the wind from escaping, removing angular momentum. And so that leads to a suppression of angular momentum loss rates, which I am quantifying here from our models. I'm showing here angular momentum loss rates as a function of multiple order. So complexity, again, increases to the right. And each triangle is a simulation. The different colors correspond to different field strengths that we tried. And these three are dipoles. And then these are quadrupoles, octupoles, and this is the angular momentum loss rate, and is in log scale. So this suppression is very large. When you go from a dipole to a quadrupole only in the large scale field, that is very easy to believe that stars could be quadrupoles, you lose 1 order of magnitude in angular momentum loss rate. So the dipolar approximation doesn't seem to be a good enough or close enough one to describe spin down. And in total, you can lose 2 or 3 orders of magnitude, which is exactly what Brown was predicting in order to get this bimodal behavior. So this explains why we observe this bimodal behavior. And in this picture, and supported by the CDI observations that say that young, faster rotating stars are more complex, stars are born in this regime where they're high in complexity, this is towards the right, and therefore they're losing angular momentum very inefficiently. And so they are in this branch. And they are persistent fast rotators. Then while they slowly spin down, because they still lose angular momentum, but much slower, they transition quickly to this regime. Quickly is because this is very steep if you consider that this is log space. This is a log axis. And this regime is the regime in which they lose angular momentum more efficiently, and they lose angular momentum how we expect them to. And that makes it no surprise that that's when they transition quickly, because this is a fast transition because of the steepness, to this branch that is the one we understand. And that's the branch we understand when we think they're dipoles. Okay, so to quantify this, we derive scaling loss based on more than 30 of these simulations. And so now we have the angular momentum losses as a function of complexity. So is the dipolar loss, whatever flux, magnetic flux you have, will put you somewhere in this line, giving you how much you would lose if the star was a dipole. And then this component here is the magnetic modulation that will tell you how far you have to go down this curve. That is given by this function. So now using this, we try including this modulation, that is what we expect really from models, into the spin-down models and see what we get. So we built a simple spin-down model by just considering that angular momentum loss is Skumenich, that is what we always expected, and there's nothing new here. C is a very well-constrained constant, is constrained by observations of the Skumenich branch and the sun itself, and this is just what you would expect from a period being proportional to t to the 1/2. And for the magnetic modulation, the scaling loss we just we derived 2 years ago, not just now, but we use that. So now we have angular momentum loss as a function of complexity. But we need to know how complexity changes with time, right, in order to build a spin-down model. Or how it changes with rotation period, because that's what stars do with time, they spin down. or with its dimensionless, we expect it to be related to the dimensionless relative of rotation period, which is Rossby number. So Rossby number is rotation period over convective turnover time. And it's just a way of getting rid of the spectral type dependency. And we do expect this to be a function. It would be nicer if it's a function of Rossby number, frankly. And so, but we don't know how complexity changes. We just know from CDI observations that younger stars, faster rotating stars, seem to have more complex magnetic fields on their surface. So what we do is we build this simple function just to try and include what observations tell us qualitatively, that n, which I call complexity, I call it n, is a decreasing function of Rossby number. This is the only free parameter we have so far in this model. The 1 is just because a dipole corresponds to n equals 1 in our model, and so there's no magnetic monopoles. And so this is true at least for young, fast-rotating stars. And then that's all we need for our model, because we're trying to explain young stars spinning down. But just to be consistent with all the observations, lately Kepler-2 observations have shown that later on, there seems to be a new deviation from gyrochronology at Rossby number around 1 or 2, by which if you observe the rotation periods of stars, they seem to be faster than you would expect for their age. And so they're losing angular momentum slower. And that, in our scenario, would mean a new increase in complexity. So we try this just to be reflecting all the observations, but this is not crucial for our model. And this is also, it's just qualitative, but it's in agreement with the growing consensus that something happens at Rossby number 0.1, where stars exit the saturation regime observed in X-rays, and something happens again at Rossby 1 or 2, where rotation periods and convective turnover times become comparable. So we use this, and this is how we build our model. These are the only new ingredients. So this is the new ingredient. Then we use the magnetic modulation that comes from models and Skumanich, and that's all there is. And so with that, we generate population syntheses for stars with masses between 0.3 and 1.2 solar masses. We take the initial distribution from Orion, so we're not starting with bimodal, with any observation that already has bimodality. It doesn't come from the initial conditions. We're using random dislocking times between 5 and 10 million years. That is the usual assumption, but it doesn't really affect our models. 5 million years are nothing in these models. And we use at each time step, we take all the physical quantities from evolutionary models here that Aaron and June is not around, but have been working on, so from the missed isochrons. So we let each star evolve with temperature, so color, and convective turnover time, the moment of inertia, every value is taken from what we would expect. And we get the following. I'm showing, in red are the observations, it's the same 6 open clusters, and in blue are our predictions. So we get pretty good agreement, especially qualitatively. We get both branches, the gap in between, and the right evolution of all 3 components. And we even get the more massive stars to transition first, as is expected. And again, I'll show you a movie of what our model predicts this will evolve like. It's nice just to see. And again, let me emphasize that we don't start with any bimodality. You'll see how it arises naturally. In red, I'm overplotting the observations where we have any. See, the gap arises from the spin-down law that we derived from models. So we're not including any ingredient to explain this. This comes from the models showing that that's what you should expect for angular momentum loss, and from the observations that tell us how we should expect complexity to change with Rossby number. And that's all. I'll take any questions.
Maybe 1 or 2 questions, and then we'll let you all get pizza, and then come back together, and we can discuss more broadly.
It seems like the models may be over-predict as
older ages.
Excuse me?
It seems like the models might overpredict at older ages for the observations. Is that true with other observations as well? And is there-
Well, that's true with scumanage
Okay.
in general. So yes, it's true that the top branch is not always fitting nicely in any models, even if you do just scumanage, it's not. But that's not the strength of what we wanted to see. We wanted to see if you do get the two branches. I think all the other details, all the other things that could fit better are related to the particular how complexity evolves with Rossby number. We're using a very naive function, just for the sake of simplicity, to show that just that will give you this qualitatively. But I can show you, we're now including for mid, this is the function we're using now, but I wanted to show you just that simple thing gives you that, because this could look like we're trying to fix things around, but we expect that in the regimes of Rossby number that are at differential rotation, like the sunlight rotation, you would have magnetic cycles, and that will bring the average complexity up a bit. And so we are including that there, and that makes things better. For example, there's some kind of a middle branch in some of the clusters that we recover with that, so it could be related to that, or to the particular shape of this function, I believe.
Well, let's thank Cecilia again. And